and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistor physics perspective. And this is lecture number 37 where we will be looking into double gate MOSFET subthreshold swing and transconductance. So, we have entered into a region where we have left behind the bulk MOSFET single gate, and now we are traveling into a region which is a double gate MOSFET as such. So, the outline of the talk will be subthreshold swing and transconductance, and we will be looking into subthreshold conduction current modeling for a double gate MOSFET and also subthreshold swing modeling. And I will also show you one methodology which was published about 2015 or 2016 by my group, which actually gives you an idea about how to analytically model the double gate MOSFET. This is the overall idea. Let's look at the effective conduction current path modeling for a double gate MOSFET. So, on the right hand side, if you see, this is the double gate MOSFET, the device. So, this is the device which we are going to look into. Double gate, this is gate number 1 and this is gate number 2, and we can actually have these as a tied gate configuration, primarily meaning that the two gates are tied together. So, whatever potential you give to gate number 1 also appears in gate number 2, and therefore, the inversion layer is exactly formed in the same way as in the top gate as in the bottom gate. However, as you are all aware by this time that the subthreshold current is primarily dominated by diffusion phenomena. It is not a drift dominated phenomena, because anyway your transverse direction electric fields are very small in dimensions. Once they are very small, you can't drag the electron very fast across it, and the subthreshold current for a double gate MOSFET is given by this expression, as you can see here, this expression here, and it goes from minus T silicon by 2 to plus T silicon by 2. So, basically this is 0 0. If this total dimension is T silicon, right, then we say that this is half of T silicon at the top and this is half of T silicon at the bottom, right. So, what we do is we say from minus T silicon by 2, which is this side, to plus T silicon by 2, we are trying to integrate to get the total current, where dN is a constant, diffusion constant which you see, LE is effective channel length, right, LE is the effective channel length which you see, and VDS is the drain to source voltage, and VT is kT by Q, which is the effective thermal voltage at 300 Kelvin, you know, it is 26 millivolt. Now, what does it tell me therefore is that if you keep your VDS approximately equal to the thermal voltage, then this becomes exponential 1, right, and exponential 1 e to the power 1 you will get, and you will get 1 minus E as the effective current. So, current drops down very low when you keep your VDS to the thermal voltage, right. And the N minimum which you get, N minimum is basically given by Ni square by Np exponential psi min by Vt. What is the psi min? This is basically the minimum surface potential, right. This is the minimum surface potential which we get at the silicon dioxide interface, where N min is basically the minimum carrier concentration which you get at this particular point. Why we are using minimum carrier concentration? Because your gate voltage is almost just below threshold, and therefore, or very near to threshold or just below threshold, where the inversion layer is still not formed, but you will have a large amount of diffusion. That is the reason we take this value and put it here. So, if you look very carefully, then if you place this value back into this equation here, then I will get Is to be equals to Q dN into Ni square by Np, right, into Le, effective channel length, that becomes your Np, integral exponential psi min by Vt into exponential 1 minus exponential, sorry, not exponential, 1 minus exponential Vds by Vt. We have two expressions, and then multiply from minus T silicon by 2 to plus T silicon by 2. Once you do that, then you get the effective current flowing through the path. So, till now we were assuming that, so let us suppose your source and drain are very heavily doped, then the depletion widths will be extending more towards the channel side, because channel is lowly doped. Then we say that the effective channel length Le is equals to L minus Ls Ld, where Ls Ld are the source channel and drain channel depletion widths. if you look very carefully, it is basically this side. This is your drain channel depletion width here, which you will find out. This will be the source channel depletion width, and you need to subtract that from your total channel length, and you need to add 2 times the Debye length here. So, the effective channel length actually is much reduced than the physical channel length, right, because of the heavy doping concentration of N and P region. Now, LS and LD is given by these two formula here, and it depends upon the built-in voltage which you see and the minimum surface potential which you see as you move from source to drain. The subtraction of that will give you the value of the effective voltage seen, and this comes from basically comes from the, you remember the width of the depletion region in a PN junction diode. When you discuss, the formula is actually coming from that particular point, right. NDS is basically the drain source number of charge carriers, NP is the number of effective charge carriers in the P region. Now, if you look at the difference between LS and LD is that there is an extra term VDS coming into picture, which is basically the drain to source voltage at the drain end, right. And therefore, this two formulation tells me that effectively that the electrostatics or the boundary conditions have to be maintained such that at the source end you will have V built in as your effective voltage at source end, and at drain end it will be V built in plus VDS will be there at the drain end, and then LD is given by the Debye length here. Now, as I discussed with you, NDS is the doping of N plus region of source and drain, and psi min basically the value of the surface potential at the partition point. Partition point is the point where you have the minimum surface potential and then it goes on increasing. So, if you plot basically surface potential versus distance, it goes to a minimum value and then it rises to a value equal. So, this is your V built in, this is your V built in plus VDS. Before that it goes to this low value here, and this is your X min here, right. Now, the point where you have X min, you need to ascertain there that d psi d min min dx will be equals to 0. What is x? X is the, look at the point, x is basically the lateral direction is the x value, right. So, x is the lateral. So, what we try to do is that we try to find out that value of potential with respect to x, which is the lateral direction, and we say that at x equals to x minimum, whatever the partition point is, the electric field is effectively equals to 0. Now, typically what we do is that if we assume that the current is flowing between T silicon by 2 and T silicon plus minus T silicon by 2 to plus T silicon by 2, then the front region will corresponds to minus T silicon by 2 to x min, and the back portion will be given by x min and T silicon by 2. You see this, as per my definition, you can always convert it. This is the back gate and this is the front gate, and then what we see is that you will get such type of electric field notational value you will get in this case. Now, let me come to, therefore, if we say that the two regions, the front region and the back region contribute separately to the subthreshold current, then the total subthreshold current IS is given by ISF plus ISB. ISF is the front gate subthreshold current and SB is the back gate subthreshold current, and these are the two equations which we get for ISF and ISB. So, just simply have to add these two together and you get the total subthreshold current here, and they are actually manipulated by the front gate and the back gate, right, and effectively gives you a value. You can ask me, at least from these expression it does not clear how come the value of gate to source voltage is responsible. Well, the gate to source is responsible for N min. You see this expression here, N min of x, this and this comes from VGS, right. So, VGS has got an indirect dependency here, right, and therefore, these two expressions VSF and VSB are primarily gate to source dependent quantities, and you do have a VDS quantity here which is directly visible to you and is given by these expressions here and here, right? And you get this expression which is there with us as the total subthreshold current generated. Now, if you do a simple manipulation and modification, we get the so what we did, we put the N min expression back into the system, and we get these two expression as ISF and ISB, where EF is the electric field due to the front gate, will be the difference in the potential divided by the distance. So, distance is x min plus T silicon by 2, and the back gate is x min minus T silicon by 2, and if you look at the potential, it is x min psi min minus psi min at minus T silicon by 2 and psi min minus psi min at plus T silicon by 2. So, it is very simple and straightforward. We are breaking the whole double gate MOSFET into two parts and then trying to find out the electric field here at the top gate and at the bottom gate. And while doing it, we evaluate the values of the electric fields at the top and bottom, this which is responsible primarily for the currents which are flowing in the top and bottom gate, right. And this is a transverse direction electric field. These are not longitudinal direction electric field, they are anyway very small in dimensions. So, this is basically the subthreshold modeling which I wanted to showcase to you. Now, let us come to the transconductance modeling. We already know that the transconductance is given by rate of change of drain current with respect to gate voltage, right. We already know this point, and for a fixed value of drain voltage. So, if you bias your device say in some region of operation, say at saturation region or at the nonlinear region, then the transconductance is given as rate of change of drain current with respect to gate voltage for a fixed value of drain voltage, right. Now, that is what is GM transconductance. And what is subthreshold swing? Subthreshold swing, we have already discussed this part, and the formula is already given to you here, but understand what is the sort of concept behind the formula. The concept behind the formula is that subthreshold swing tells me how much amount of gate voltage change you need to do in order to have one order change in the drain current, right. Say if I write down my subthreshold swing to be equals to 60 millivolts per decade, it effectively means that for a 1 decade change in current, say 10 to the power minus 6 to 10 to the power minus 5 amperes of current, how much amount of VGS I have to change, that is defined as this thing. In this case, for example, so for a 1 decade change in the current, I want 60 millivolt change in my gate voltage. At 300 Kelvin, the ideal value is one cannot go below 60 millivolts per decade, right. That is a standard. There is a reason for that. We have already discussed this point possibly earlier, but if not, you can have a look into standard books available there. So, the minimum value for a bulk MOSFET at 300 Kelvin is 60 millivolt per decade, and we cannot go below that, right. And where this current is basically my diffusion current or the subthreshold current which is flowing, right. So, the subthreshold current, as I discussed with you, is primarily because of diffusion phenomena, and it is always proportional to the carrier concentration, right. When I say virtual cathode, I mean to say the source end which is there, and therefore, the subthreshold swing is given by this expression in terms of charge potential, and it is also referred to as this value, and it gives me a rather complicated looking equation which is subthreshold slope, as you can see here, depends upon all these things which you see here. Now, Vt is fixed at 300 Kelvin, other variables are there, fix in the value of variables and you can get the value of the subthreshold slope. That is the reason why we define this to be as a subthreshold swing in case of a double gate MOSFET here. Now, let me also now come to a brief idea about the analytical modeling of a double gate MOSFET. So, give you the expression here, analytical modeling of DG MOSFET, right, using taking Gaussian profile, right, and I am taking this from one of our research group's research paper, and this is basically TED transactions, IEEE transactions on electron devices, and it was published in November 2013, right, 2013 IEEE transactions on electron devices with my co-authors. How the analytical model proceeds is very simple and straightforward, right. What we do is, I will tell you what we do is, the device which you see is the device under study is exactly the same thing, this only, right. So, what we try to do is that we assume that the potential which is there, the potential within the device, right. This is not a subthreshold modeling, this is primarily a modeling of the drain current. So, we say that it is assumed that the potential within the device is basically parabolic in nature, right. Parabolic in nature in the sense that I can write down, therefore, the potential which is a function of x and y can be written as a of x plus b of x y plus c of x y square, right. And so, if this is my double gate MOSFET, as you can see, this is my drain and this is my source end, then we define what is x and y. We need to showcase that as well. This is your x, right, and this is y. So, what we are assuming is that as the potential moves from the source to the drain end, it is parabolic in nature. As you can see, it's y square, sorry, I am sorry, it's x square dependent. So, as you move from top gate towards bottom gate, you have this y square dependency available with us, right, and that gives me the value of the surface potential value. So, Ax, Bx, Cx are coefficients. These are coefficients which can be determined by the boundary conditions, right. They can be determined by the boundary conditions. And what we found out using that, and we used a Gaussian profile, and what we found out from all these discussion was that the final value of the potential which we got was that the final value of the surface potential value which we got was given by psi of f was approximately equals to C1 e to the power minus x by lambda plus C2 e to the power x by lambda plus some integral, right. And this gives me a expression for how a potential varies within the value. The C1 and C2 are constants which are depending on the structural value or the structural dynamics of the double gate MOSFET here. Now, now if you take up this double gate MOSFET and you try to solve it, and if you try to plot the surface potential with respect to the distance x, then we get something like this, that we get like this, and it goes to down and then it goes to the top. So, you see, near the channel edge the electric field suddenly rises down, because the rate of change of psi with respect to x gives you the value of the electric field along the longitudinal direction. So, the electric fields can be seen in a double gate MOSFET to be steeper near the drain end as compared to the source end. Makes sense also because source is generally for all practical purposes grounded, and you apply a voltage here which is VDS, right. So, when you apply a drain to source voltage here which is VDS, the electric fields become steeper and steeper near the drain edge, right, and therefore, the potential varies very fast in this case because of high rate of change of voltages near the drain end. However, if you go on increasing the voltages at the drain end, which means VDS is larger and larger, then you will see that this goes much more further to the top, right, which means that higher voltages will entail a larger longitudinal current, will increase the value of current flowing through the device because of a larger electric field. Now, we also found out in this paper the threshold voltage of the device. How do you define threshold voltage? That gate voltage at which the channel is inverted, right, inverted as it becomes as much n type as it was initially p type, right. And we found out the threshold voltage expression as the threshold voltage, I can write down voltage, and we found out that VTH was given by VFB, the flat band voltage, plus 2 phi f. This is coming from your conventional understanding that it should be twice, the surface potential should be twice going down. Therefore, this minus C1, right, the maximum of exponential minus x min by lambda minus C2 exponential minus plus x min by lambda plus lambda square q Na minus minus NSD plus x min divided by epsilon silicon, where phi is what? Phi is kT by q. So, it is Vt ln of Na by Ni. This gives you the value of the threshold voltage expression which gives me. Now, this threshold voltage, if you see, it depends on the value of x min which you see here. It depends upon the x min value, and it also depends upon the NSD min, which means that how doping has been done in the source and drain region will also affect the threshold voltage of the device, right? And if you look very carefully to your previous discussions on bulk MOSFET, this was not coming into picture. So threshold voltage is now becoming a function of the biases. Not only bias, it also depends upon the doping concentration of the source and drain region in this device. When we plotted and then we found out the total current in the linear region and saturation region. I will not like to draw the expression for the whole one, but I sat, which is the saturation current, was seen to be proportional to the overdrive in a device, and this was true as well. We have already seen that the saturation current is always proportional to overdrive, and it also depends inversely upon the effective channel length. So there is a W by L term in the I saturated region. So I will just write down for one, you give you one term. It is 2W mu times Cox divided by L effective channel length minus diffusion length plus F by EC. This is a constant. EC is the saturation critical electric field which we get, right, plus lambda times A times 2W Cox L effective minus LD square, and so on and so forth, and multiplied by some voltage value here, which means that this W is still in the numerator and L is actually in the denominator. So basically in a double gate MOSFET, the drain current is still proportional to W by L, the aspect ratio. So higher the aspect ratio in a double gate MOSFET, more will be the current flowing through the device. It is also again directly proportional to the value of mu, which is the mobility of the charge carriers, right, and gives you a effective value of the total current which is flowing through the device. So we also found out the variation of threshold voltages. So there are two ways of which we can do a doping. One is constant doping, right, and we can do constant doping. We can also do what is known as a Gaussian doping, right, Gaussian doping. Once we do constant and Gaussian doping, we can get expressions. We also did what? We tried to find out the variation of delta Vt, or the variation of threshold voltage delta Vt, as a function of the standard deviation of the Gaussian input dose. And we saw that as the sigma value goes on increasing, which means that as the sigma value increases, the value of your threshold voltage actually starts to drop down. And this was quite interesting, and we saw that therefore that if your Gaussian has got larger sigma, it effectively means that if I have a Gaussian surface, effective sigma is, this is very low sigma, right, this is very low sigma. Effective sigma means something like this. If it is flattened out and the sigma value is large, but the mu value, which is, this is the mu value and this is the sigma value, if the sigma value is relatively large, you will have a lower threshold voltage to work with. Think about it, why is it like that, right? And incidentally, it does not, it obviously depends upon the dose at which the Gaussian profile has been made. So this was done by our group, and you can find this in this research paper in a much more detailed manner, those who are working in this domain. Let me then come to the next part, and which is basically my small and large signal modeling. I will just introduce those. We will do a discussion on large and small signal models, and then we will go for a small signal non-quasi-static analysis for a double gate MOSFET. So primarily when you look into double gate MOSFET, we have finished now with subthreshold expressions. We have also looked into the methodology of analytical solutions of double gate MOSFET, both at saturation and linear region. Now we come into a region that if I am given an AC signal, then how can I extract the conditions, effective conditions, by doing a analysis. The two main analysis methods are large signal analysis and small signal analysis. Large signal primarily means that so if the signal is large, it effectively means that the gate voltage which you are giving is varying to a large extent, right? It's moving very large. Once this is moving very large, then the nonlinearity of the transistor must be taken into account, and that is what is written here in the first expression here, where the nonlinearity of the device is taken into account, and therefore the large signal analysis is mainly used to find the bias condition of the circuit. Now when you go for a small signal analysis, a linearity is always assumed, because if I assume a large signal, then the variation is so large that that I have to take nonlinear. But if you take small signal, then for a small region it is still a linear region, right? It's still a linear. So I can break down a small signal analysis into linear conditions of the MOS device, whereas for the double gate MOSFET, whereas for a large signal I need to actually take up the large signal analysis, which means that nonlinearity will come into picture. Now, these are the two major sort of analytical approaches which people do as far as double gate MOSFETs are concerned. In fact, it is applicable to all the devices. Now, there has been quite a large number of research papers which have worked with both small signal as well as large signal analysis, and they have used either quasi static analysis or non quasi static analysis. I will come to that later on, but for the time being we are assuming that our devices are all long channel, right, which means that the distance between source and drain is quite large, and we are also assuming the device to be symmetric in nature, which means that both my top gate and bottom gate made of the same material, same thickness, everything else is same. It is just that one is the top gate and one is the bottom gate, right. And we will be using some charge based model known as EKV model to explain to you the quasi static and non quasi static phenomena. EKV model is basically based on formalism is based on E is a scientist known as Enz, and this person by Vitos, right. Enz and Vitos model, which charge based model is there, and it is used very often in device modeling, especially in double gate as well as bulk MOSFET. So, with this let me stop here today, and what we learned is two things we have learned now: subthreshold modeling of a double gate MOSFET, where we understood it is diffusion dominated. We also did a small analytical model, more details can be found in that paper. Small signal analytical model was developed. Then we just entered into the basic idea of double gate model with both large signal analysis and small signal analysis. And what we will be doing next is use this small signal and large signal to develop the further equations for the double gate MOSFET, right. So, with this let me thank you all for your patient hearing. We will take the next lecture starting from here itself. Thank you.